after seeing all the talks after mine yesterday that did sophisticated QI things, I realized maybe I could have gone faster. So we'll try to accomplish that today. But if I go overboard in that direction, just let me know and I will slow down again. So essentially where we stopped was I was trying to discuss this question of, so we given a space X, right, understand groups gamma qi to X. And I had suggested that the one way to do this was to think of gamma as quasi-acting on X. So just to remind you, that just meant each element of gamma comes equipped with some quasi-isometry of X to itself. The constants are all uniform across all the elements of gamma. And the compositions behave exactly the way you expect them to for a group action up to bounded distance. Okay. So, right, so how we're going to do this, of course, depends on what X is. And a good place to start is how you understand groups honestly acting on X, whatever this X might be. And the approach here is sometimes topological, sometimes geometric, sometimes analytic, just depending on what space X you're looking at. So let me start with some sort of topological considerations. And before we deal with some big group quasi-acting, we're just going to want to deal with individual quasi-isometries. Just as if you want to understand groups of isometries of hyperbolic 3 space, you usually want to start by understanding what individual isometries look like, and then trying to piece that together. So something I wasn't so careful about last time is that, in general, the exact map we have as our quasi-isometry is not really important. It has a lot of arbitrary choices built into it. So for example, when we took R2 being quasi-isometric to the integer lattice by just taking each point in R2 back to some closest integer point, there are points that are equally close to two things we have to pick. It doesn't matter because it all gets swallowed in the less than or equal to something plus C in the inequalities for quasi-isometries. But part of what this means is that we'll generally think of two quasi-isometries that are just bounded distance perturbations of one another as being essentially the same. Okay, so let me write that down as a definition. And this doesn't have to be from a space to itself, just from any space to any other space. All right, so this is our equivalence relation. And when I talk about improving individual quasi-isometries, what I really mean is I just want to pick a nice representative of the equivalence class that respects whatever sort of structure we know about on X that we're trying to use. So So one version of this, well, I'll write the hypotheses later, the so-called connect the dots argument, which is essentially finding a nice topological representative for your quasi-isometry. Okay? So we think of X as, say, some simplicial complex. and we have some quasi-isometry from x to y. So here's x all cut up into nice simplices that they said, well, generally, unless I say otherwise, be assuming all of our simplices are metrized as regular Euclidean simplices of side length 1. So it doesn't really matter from the course point of view. We're mapping this over to some space y. Well, the first, maybe I can take advantage of colors other than just randomly switching from one board to the next. If all of these simplices have side length 1, then every point is within one of a vertex. Right? So the vertices fill out the whole space pretty uniformly. And in fact, this is just going backwards from how we built the, say, the graph to approximate x yesterday. So these vertices go wherever they go. And that's a perfectly good continuous map on the vertex set, since it's discrete. Now, what happens along some edge initially is nearly random. Right? These edges only have length 1, and because of these additive constants in the definition of quasi-isometry, what happens on that scale is essentially arbitrary. So what I know about this set, if maybe those vertices map there, I know they're not too far apart because I can't stretch distances too much. And then I know that this red edge, all the points along here are within one of these two vertices, in fact, both of these vertices. So they end up somewhere nearish this thing. But the point is, I can simply change my map to instead map that edge to the geodesic segment in a nice, say, constant speed parameterized way. And I haven't actually done anything on any large scale. All I've done is move a couple of points that were within one over there, some constant over here of the endpoints, around to some different points that also stay close to these two things. Okay, so nobody stops me from doing this, and I can do this to all the edges, and it just replaces my map by an equivalent map so far. Where we get into trouble, potentially, is if we try to keep doing this. So now I have that 2 simplex over there, whose boundary I've mapped across just by leaving the vertices where they were and mapping the edges to geodesic segments. And what I have initially, again, is essentially a random map that sends points in this simplex to somewhere near these 3 points in an essentially arbitrary way. What I would like to do is instead just replace it with some nice, say, piecewise linear map from this simplex to something over here. And the problem is I need a something. Okay. So when I had to just connect 2 points that were close together, I was guaranteed there was a path that ran between them that wasn't very long. That's basically built into the fact that my space is a geodesic metric space. But the higher homotopy versions of that don't come for free. Okay, I have here a loop, which I have now mapped over here continuously to a fairly short loop. Okay? And I need to fill it in with a small disk. If I want to extend this map continuously without moving it very far from my initial map, I need to find a disk to fill in this loop that doesn't go too far away from these points. Okay? So there's a definition here. All right, I guess I better give the definition in terms of y because that's where it's relevant. So a space y is uniformly contractible here is going to mean that for any radius little r you want to give me, there exists some bigger radius r so that for all y and y, the map from the ball of little radius r around y to the ball of radius big R around y is null homotopic. Okay, so this doesn't just say that the space is contractible. It says, in fact, if you give me something that you want to see contracted of some bounded size, it is in fact contractible without going too much farther away than that, in a way that doesn't depend on where in the space you're looking. Okay. You can, of course, cook up versions of this for uniformly 1 connected, uniformly 2 connected, uniformly 3 connected, and so forth. For example, what we needed here to map our two-dimensional simplices across is that every short loop contracts inside some ball that's not too much bigger than its radius. So this is a property that a space, of course, may or may not have. In particular, it implies it's contractible. So, but an example, 2 examples to keep in mind maybe. It's a different issue. Okay, if you just take some infinite strings of disks of some fixed radius touching each other at a point, this is a perfectly good contractible space. In fact, it's uniformly contractible, and there's no issue. But we can take what is topologically the same space and just change the metric on these disks to make them sort of run away from the boundary a little bit. And you can think of it as again, what is homeomorphically the same space, just a bunch of disks, but where we metrize the disks to be these bumps that are going higher and higher and higher as you move out. And then as you look in this space, you see these circles of fixed radius that are the base of these circles, where you have to go farther and farther away from those circles to actually see that they're trivial in pi 1. And if you have a space like that, you can run into trouble trying to fill in these cells. Okay, so let me make a fairly simple observation, though. If y is contractible and has co-compact isometry group, so there's, of course, again, there's a simplicit finite dimensionality, et cetera, assumption in here that I didn't write down again. But the point is simply that contractible tells me, of course, this ball contracts, is null homotopic included into the whole space. I can form the null homotopy. That's a map of a compact set in. So it sits inside something of some diameter. Okay. But there's only a compact family of balls to worry about up to isometry. So the radius at which that happens can be chosen uniformly. Okay. So this means in particular this is a terrible way to write this, but if you have a finite aspherical, compact aspherical space, then its universal cover well, by definition, it's contractible. And because the quotient by pi1 is compact, it has a co-compact isometry group. I didn't write a statement. So when I said there are things, we pick a space X we like for some reason, this is the kind of thing we might like about our space, although somehow now we're calling it Y. So if the space we're dealing with, we're interested in because it's the universal cover of some compact, a spherical manifold or some other space, then it is going to be uniformly contractible. Okay. And what I started sketching over here is that if X is, say, finite dimensional, and Y is uniformly contractible, so if our target is uniformly contractible, we can improve our quasi-isometry to make it continuous, okay, which means a lot of topology that you see in these spaces is actually implicitly QI invariant. And in fact, we may need this later. I'll point out I never really cared that the map from X to Y was a QI. In particular, I never cared that it has an inverse. All that was important over here was that it didn't stretch distances by too much. So the upper bound on what it could do was relevant. The lower bound is only relevant in trying to build an inverse map. I mean, certainly a CW complex, as long as the cells are of metrically bounded size, the same argument works in exactly the same way. If X is more exotic, you have to be a little bit careful about what you mean by contractible, and so forth. So, I mean, I guess I should point out, maybe I should have said this yesterday, if you give me any geodesic metric space, right, I can pick any positive radius you like and find a maximal packing by disjoint R balls. The corresponding balls of radius 2R then cover the whole space. And if you form this sort of intersection graph, the nerve of the covering by these two balls of radius 2R that we talked about last time, that's always a simplicial complex that's quasi-isometric to X. Okay, so as far as the quasi-isometry stuff is concerned, we may as well assume our X is simplicial. In fact, we can often take it to be just the vertex out of a graph or something. But all right. So, the consequence of this is that, okay, again, in the setting of simplicial complexes or reasonably locally tame topologies for X, if we're dealing with things which are uniformly contractible, which we often will be if we're looking at groups with finite k pi 1s, then certainly QI implies proper homotopy equivalent. Okay, and the picture is essentially what we've said. We take our pair of quasi-isometries that are approximately inverse to one another, okay, replace them with continuous maps, which we can do because these spaces are uniformly contractible. Certainly they're quasi-isometries, so they send balls to not too much bigger balls, so the maps themselves are proper. And then what about the composition? Well, the composition this way, more or less by assumption, I always get this wrong. This is g of f of x. Okay. This distance is always at most c, or whatever the constant we wrote down for the quasi-isometry. Okay. So this composition, which is the self map you get by composing the map and its supposed inverse, moves points not very far. Okay. So think of this as a map. So if you think of this as partly defining some map for you from x cross I to x, where we have the identity at the top and g composed with f on the bottom, the fact that it's bounded distance from the identity means that this is a quasi-isometry from all of x cross I, which of course is also quasi-isometric to x. So again, approximated by a continuous map. Or if you want, just repeat the content of the argument to see that because balls are uniformly contractible and x and g of f of x are uniformly controlled distance apart, we can homotope them. Okay. So this composition is guaranteed to be homotopic to the identity. And in fact, more than that, it's guaranteed to be homotopic to the identity with tracks of the homotopy not very long. Okay. We're not perturbing our map very far to do this. Whatever the original distance between g composed with f and the identity, whatever this larger r is, all of our homotopies can stay inside of that with tracks of at most that diameter. So you can in fact say a lot more than proper homotopy equivalent. And if you want to set up some whole fancy algebraic topology machinery controlled by metric spaces, you can. But often just proper homotopy equivalent is enough to get a lot of interesting information. Okay, so this tells us that a lot of topological invariants are also quasi-isometry invariants. So for example, if pi has a finite k pi 1, then say the cohomology with compact supports and in fact, this finite k pi 1 assumption is somewhat artificial here. We need that to do this all at once. But if you just want to do things on the k skeleton one at a time, it will get you what you need about cohomology. This is, I guess, if you're a group theorist, this is the same thing as that. Now, you only get this isomorphism from a QI in the proper homotopy category. There's no equivariance left. So you don't get any Z pi module structure out of this. But you do get some things being invariant. Things about dimension and the like are also invariant. Anything you can write down in terms of proper homotopy type, you can read off from quasi-isometries. So in particular, we've seen people talk about ends already. We're just talking about the connected components of complements of larger and larger compacta. Or if you want, you can read it off of the compactly supported cohomology. So whether your group is one-ended or two-ended or three-ended, although good luck, or infinitely many-ended, is a QI invariant. Right? And then there's, of course, this famous theorem of Stallings that tells you whether your group has more than one end, tells you whether it splits. Okay? So a consequence of this via Stallings is that whether a group splits over a finite group is a QI invariant. So if I mentioned I would say something about geometrization in three manifolds. So let me just quickly point out that for M compact, let me just say a spherical three manifold. I can never remember what the other words the three manifold topologists use. I don't going to mean that. In any case, we can split it. Well, I don't even really need that. Okay. So we can split into pieces. I don't want to go into detail here along S2 and T2 with the resulting parts geometric, okay, which here means modeled on, and I'm sure I'm going to leave one of these out, S3, S2 cross R, R3, R cross H2, SL2R tilde, H3, nil, and sol. Okay, so yes, the count right. All right, so in any case, if you think about this as trying to be some generalization of uniformization for surfaces, okay, we have to cut up our manifold first, okay, and then the resulting building blocks that we get have these various types of geometries. Okay. So if we want to, say, be able to apply this QI machinery to understanding what's going on for three manifolds, we want to know that the way these things split up is QI invariant, and then we want to know something about how QIs work for these individual geometries. Okay. I'm not going to go into this in detail, but I'll use these as motivating examples for a bunch of things I want to discuss. And this is maybe the first hint that some of this splitting part is going to be okay. The splitting, at least on two spheres, right, is just free products. Okay? And that is at least up to allowing finite groups instead of the trivial group QI invariant. All right, but right, we would really like to know more. We would like to know not just that whether you split as a QI invariant, but then the pieces that you split into are then QI, and so we can induct, so forth. That's going to take more work. All right, so right, just to talk about group splittings for a minute, right? We have this sort of Bass-Serre theory dictionary. Let's say with finite quotient, maybe. Right, so splittings of groups give an action of the group on a tree and vice versa. It's just a slightly more geometric way of encoding the combinatorics we're talking about in a group splitting. I guess I should draw at least one picture here, just from right, if your splitting is coming, say, from an application of Van Kampen's theorem, And when we look at the universal cover, as we saw before, the list of these geodesics are just a bunch of, list of this curve is just a bunch of geodesics up here. And each thing has a red side and a blue side. And the dual to this picture is just the tree that we're talking about. So if you have not seen Bass-Serre theory before, that is the world's most useless introduction. But that's where the tree comes from. In some sense, the content of Van Kampen's theorem is that this is a tree. All right, so So here's one way of putting sort of the basic question about QI invariance of splittings of groups. If you've got a group that you know it acts on some tree, so it has some splitting, and a group which is quasi-isometric to it, do we expect it to also act on a tree, probably in some similar way, so that the various groups we're splitting into are also QI and so forth? And the answer in general is probably not. Okay, without any extra knowledge about how the splitting works, we can't really say very much. All right. Right, I guess one can think about triangle groups, which can't act on any tree at all without a global fixed point, but they even have finite index subgroups, which are surface groups, and then split in many, many ways. Okay, so even commensurability doesn't quite respect this, much less more general QIs. But there are a number of cases where something can be handled here. So sort of step 0, and this is the step that usually doesn't work. So we said last time if gamma prime is QI to gamma, then gamma prime will quasi-act on gamma itself. Okay. Now gamma prime also acts on a tree. We might like to get this gamma prime to at least quasi-act on that tree. Okay. And if you think about what that means in a picture like this, if this is our gamma that has a splitting, and then we have our mystery gamma prime that's pushing this picture around by quasi-isometries, what we want to know is that these blocks are actually QI invariant, and they just get permuted when we push this picture around via QIs. In this case, there is absolutely no reason for that to happen. Okay, a quasi-isometry of the hyperbolic plane, even an isometry of the hyperbolic plane, can move this set of geodesics completely off of itself, give you a totally different decomposition of the hyperbolic plane. All right. So we need some reason to think that this will happen, which generally means we need some sort of intrinsic characterization of the thing we're splitting over. Okay. So for example, in Stalling's theorem, where we're splitting over finite groups, what we're seeing are bounded sets which disconnect the whole space. So a compact set whose complement is disconnected and unboundedly disconnected, separating ends. Okay. And that's something that you can sort of talk about in terms of proper homotopy theory and hope will be QI invariant, because we can push a lot of proper homotopy theory across. We've seen a couple of talks yesterday that also mentioned examples of things like this. So if gamma is one of these generalized Bompsog-Solitar groups, okay, in this terminology, that means we're talking about something which acts on a tree Okay, so if you remember, we took some circles, and we glued on annuli via finite coverings of the circle. Okay, pi1 of the circle is z, so all of our vertex and edge stabilizers are infinite cyclic here. And the inclusion of each edge stabilizer into the vertex stabilizer is finite index, because it's a finite degree covering. Okay. There aren't really so many other inclusions of z into z anyway, but so if you draw the universal cover of the complex that was mentioned in this talk, what you see topologically is I'm not going to be able to do this very well. Something that looks so the universal cover of these annuli are just giving us strips. The universal cover of the circle are just giving us lines. And so we see finitely many strips glued on along each one of these lines. We see something that's essentially tree cross R from a topological point of view. Okay. Metrically, it's a little bit not, unless you happen to be in this unimodular case. It's more or less exactly what unimodular means. Because if you remember, this annulus is the universal cover of some the strip is the universal cover of some annulus here, which glued by degree n on this side and say degree m on this side. So what does that mean in terms of fundamental domains? Well, when you draw the universal cover, you're cut up into little strips, but somehow in a fixed unit length of the circle here, you see n, m. And on the other side, somehow in the same distance, you're seeing n, which I drew quite poorly. I should draw it more accurately, since all I seem to want to draw today is the hyperbolic plane. I continue to do that. You can think about this strip as being a region between two horoballs in the hyperbolic plane, where the sort of natural closest point projection from one side to the other is actually stretching or collapsing distances by a factor of n over m. Okay, so that you see n things on one side and m things on the other side, tracing out what is essentially the same piece. Okay, and what that means very quickly in terms of the geometry of this tree cross R is if you look at a ray in the tree or a line in the tree crossed with R, so it's topologically in R2, you may in fact be building yourself something which is metrically quasi-isometric to the hyperbolic plane. You might be building something which is quasi-isometric to R2, just depending on whether n and m are equal or not. Okay. So this is sort of geometrically what that unimodularity condition means. And it tells you that the model you have is coarsely tree cross R as a metric space instead of just topologically. All right, so that's okay. So now the point is, in tree cross R, from a proper homotopy theory point of view, these vertex of tree cross R lines are special, right? They're properly embedded lines that disconnect locally into 3 or more pieces. Okay, if you take a line that runs down the middle, you only see 2. If you wander around and come back, you have to think for a little bit, but often you don't disconnect at all. Okay. So I won't get into the details of this proof, but the point is that these tree directions are sort of topologically intrinsic. So the fact that you have this splitting is something you can detect from proper homotopy theory type considerations. Okay. I think initially this was done by pointing out that the line and tree cross R, which are topologically R2s, are essentially the only carriers of nice two-dimensional homology classes. So you pick those out, and then you look at their intersections to get the strips. But there's now a lot of ways of pulling this out of the course topology. All right, the other example I think we saw yesterday, which I'm going to have even more trouble drawing, but I guess it's again the hyperbolic plane. Where we had surface glued to some other surface. Okay, along some curve. This is again a splitting now. Surface group, free product surface group amalgamated over Z. And the universal cover again. Right, we had this picture of the hyperbolic plane with this pattern of geodesics, and then coming out of each one, I should make the speaker come up and do this because I can't, but we had a nice transverse hyperbolic plane, and then on each of those there was another one through each of the corresponding geodesics and so forth. So you have some sort of tree of spaces built out of hyperbolic planes. And again, these Z's where these lines where things branch are sort of topologically intrinsic, and you can pick them out using course topology. Okay. So maybe I don't want to say anything more about step 0 because it's idiosyncratic to exactly what splitting you would like to be QI invariant. Sometimes it is, sometimes it isn't, and if it is, you have to figure out why and then pull it out of the geometry. Okay, but once you get, say, that your QI has to send lines like that, at least close to lines like that, all you get is exactly what we wanted to get in step 0. Every individual element of my mystery group now acts by a quasi-isometry on gamma. Those quasi-isometries have to preserve at least approximately this decomposition pattern, and so they induce a quasi-isometry of the resulting tree. Okay. And if you put it all together, you get some quasi-action of your mystery group on a tree. Okay, so here's an older theorem. This is with Mosier and Segev. So if you have a tree like the ones that come up for these generalized Baumschlag-Solitar groups, which is itself a locally compact proper geodesic metric space, which more or less means we can only have finitely many edges at each vertex, then in fact anything quasi-acting on it can be made to act on a slightly different tree. Okay. This is really leans heavily on the proof of Stalling's theorem. Essentially, I won't say a lot, but the first step is to get G to act on some simply connected 2 complex, which is quasi-isometric to the tree, and then use this machinery of minimal tracks to find a G invariant decomposition of that 2 complex to get then a dual tree that you act on. Okay. So this is in some ways helpful. For example, in these generalized Bohm-Sauer-Solitar cases, this tells you anything quasi-isometric to a generalized Bohm-Sauer-Solitar group will act on some finite valence tree with virtually cyclic edge stabilizers and finite quotient. You don't quite get Z, you only get quasi-isometric to Z for the stabilizers and so forth. So at least with that slight enlarging of the category of generalized Bohm-Sauer-Solitar groups, anything that is Qi to 1 is also 1. This is a nice sort of class of groups. They're not all Qi to one another, so there's more work to do to figure out what's going on there. But this also gives, even in the simplest case, an example I promised, I think, last time. So this is, I mean, while it follows from that theorem, this is older. Okay, or maybe I should say it this way. As I said, this follows from that one, because if the free group is itself quasi-isometric to a tree, so a group quasi-isometric to the free group is then quasi-isometric to a tree, so it quasi-acts on the tree. This theorem then tells you it actually acts on some other tree, and this thing I didn't talk about very much about this Qi is approximately equivariant. Tells you that the fact that the original action was proper makes the new action proper. So it gives you a graph of groups decomposition of the mystery group into finite groups. Okay, but it's an older theorem that such things are all virtually free. And in fact, virtually free groups are essentially the only groups of dimension 1 in an appropriate sense. And so you can even pick it off of the proper homotopy invariant statement in some older group theory theorems. All right, so what? This is a theorem. But put a both in here. Okay, so every virtually free group acts properly and co-compactly on a tree. But if you pick two different virtually free groups, there is no guarantee that there's one tree they will both act on. Okay, it's essentially something like you take free product of ZP and ZP versus ZQ and ZQ for different primes. And the point is the fact that you have to these finite groups have to stabilize vertices then tells you something about what the valence has to be at the vertex. Okay. And these just can't simultaneously work out. Now, again, this was known well before, I think, the word quasi-isometry came around, at least if you interpret it suitably. But it is also true that these G and G prime cannot act properly and co-compactly by isometries on any x. So this is still proper geodesic, etc. Okay, so it's not just trees that they can't simultaneously act on. In fact, and we said if you act simultaneously co-compactly by isometries on the same thing, then you're QI. I'd mentioned the converse is not really true. This is an example, okay? And the idea is an important one for things we'll talk about mostly next time, I guess, right? Right, if they did, G and G prime would be sitting inside of the isometry group of this mystery X. Okay? And if we let gamma be the group they generate, this is some group of isometries of X. Now X is necessarily quasi-isometric to a tree because it's quasi-isometric to each of G and G prime, and they're virtually free, so they're quasi-isometric to trees. And then this theorem over here would tell you that this mystery group gamma actually acts on some tree again. It's a group, it's quasi-acting on a tree. So it would act. It's not a proper action, of course. It's presumably some crazily dense thing, but it's still going to act. And of course, this would have G and G prime. Since they're just both subgroups of gamma, if gamma acts, they both act. And again, this approximately equivariant statement tells me that since both the G and G prime actions inside of gamma were originally proper and co-compact, they remain proper and co-compact after we change our approximating tree a little bit. Okay, so the fact that they can't act on a tree actually means they don't act on anything. Okay, and this is, in fact, in some sense, the general approach to understanding how true or not this kind of statement is and what the good models for a given geometry are. If you have a space X you like, its full isometry group acts on X by isometries, so it too quasi-acts on anything Qi to X. And if you can understand what those groups look like, then you can say essentially what all the kind of maximal geometries are. And there's some follow-up to that paper we wrote where we sort of precisely enumerated what all the trees are that have maximal symmetry groups. So everybody acts on one of them, but not necessarily the same one. Yeah, so close to out of time. Let me just maybe say in words, the QI classification of the generalized Bohm-Saug-Solitar groups is actually kind of intricate and a bit surprising. Okay? They're not all quasi-isometric to one another. The ones that are unimodular, that are tree cross R, are all quasi-isometric to one another, and in fact all commensurable to free group cross Z. The non-unimodular ones split into essentially two cases. Well, there's the solvable ones and the not solvable ones. The solvable ones are linear and reasonably well behaved and quite rigid from a QI point of view. They're essentially quasi-isometric only to their finite index subgroups. And then weirdly enough, all the other non-unimodular ones are just in one giant QI class and all quasi-isometric to one another. And somehow that's the tip of some sort of iceberg. I guess maybe the even tippier tip part we saw at the beginning, which if you take, in terms of group theory, if you say repeatedly start taking free products with Z, okay, the trivial group is the trivial group. You take a free product with Z, now it's Z. That's fine. You take a free product with Z again, now it's the free group on two generators. If you take the free product with Z again, okay, now it's the free group on 3 generators, but that's commensurable to the free group on 2 generators. Somehow, any more free producting doesn't change the large-scale geometry anymore. Same with surfaces, right? You have the sphere, and then the torus, and then the surface of genus 2, and more handles don't really make a difference from a large-scale picture. Okay? And somehow this Baumsug-Solitar thing is a similar kind of case. All right, I was going to say something about the surfaces glued along curves, since we saw a talk on that last time as well. There, unfortunately, I said the step 0 works. The splitting is fine. This theorem doesn't apply because the splitting is infinite valence, because the inclusion of a curve into a surface group is infinite index. So you have to do some version of this for infinite valence trees. And we have some results in that direction. I won't even try to write them down because they're quite technical and contingent on exactly what the splitting looks like. Because unfortunately, the analog of this for infinite valence trees is just wildly false. Okay. And yeah, people want to see examples. I'm happy to discuss them, but they're. The case where the things you're gluing are manifolds and what you're gluing along are submanifolds, okay, does work out. Okay? If you have Poincare duality for all the gluing pieces, then somehow the separation properties of Poincare duality things allow you to pick off the components again in a nice enough way to get what you want. And so, for example, anything Qi to one of these 2 hyperbolic surfaces glued along a curve is going to be a finite graph of groups with each of the vertex groups virtually a surface. It could be some orbifold. Okay? And all of the edge gluings virtually cyclic, not necessarily actually infinite cyclic. But as with the Baumsug-Solitar case, I imagine understanding exactly which such things are Qi to which other ones is probably pretty delicate. And I will leave that to people who've thought more about those groups. So maybe that's all I want to say about the splittings part of the picture. Next time I want to start talking about some of these more classical geometries, lattices and Lie groups, and how their quasi-isometries behave, which if you think of this as some sort of coarse topology, that really doesn't work in those cases. We even saw already there's nothing topologically that's going to distinguish the hyperbolic plane from R2. We needed something geometric like growth or whatever. And for all, say, of these higher or any non-compact symmetric spaces, of course, they're all just Euclidean space topologically. So there's a lot of sort of large-scale generalizations of curvature and what's more properly coarse geometry that goes into that. All right, and I'll try to address that next time and maybe mention what happens for some of those. Okay. Thank you. Right, so let me, so if you just want the Baumsug-Solitars, it's easier. The other ones look roughly the same. And I may have left out a few extra trivial cases. Right, so for BSMN, right, this is this group. And the picture you're looking at here is the tree we're acting on. Is sort of a homogeneous tree with n and m edges at each vertex somehow distinguished. There's the ones coming in and the ones going out if you want to orient it. Okay. So if m and n have the same absolute value, then we're in this unimodular case. And we're dealing with something which is virtually a free group cross Z. Okay, so it's just the standard product geometry from the large scale point of view. So BSMN, right, is solvable and well linear and otherwise well behaved. I guess I'm going to assume the absolute value of m is the smaller one. So if the smaller number is 1 somehow, then everything is well behaved. You have a tree which somehow consistently just branches in one direction, and it makes a big difference in the geometry in the end. Okay. So essentially, you can just think here, BS1n has an index 2 subgroup that's BS1n squared. Just conjugate by x twice, and now you've gone up to. And this continues. So these things are commensurable as soon as you can find a power of n and n that are equal. Okay? And that's exactly when they're quasi-isometric. This, I don't know who it's due to. It's fairly immediate. This is Farb and Mosier. And then all the others are in one QI class. So somehow once you have branching both in the upward and downward directions, it doesn't matter at all how much there is. Okay. And these, if you like, these are even more robust examples than these virtually free groups. Because not only are they QI and they don't act on anything in common, they don't virtually act on anything in common. Here you can fix your problem by passing to a finite index subgroup. Here, these things are wildly not the same algebraically, and there's nothing you can do about it. Oh yeah, this was me. And I guess I will say that, in fact, you can replace z by z to the n in this discussion, and everything works out basically the same, except this last class, there's something more complicated, and I've been trying to give an open problem every day, so now you gave me an excuse. Okay. There's an intermediate thing between being commensurable and being QI. It comes up in this classification here. You could talk, say, about if you have two groups inside, say, of GLNR, right? R, I'm not even sure what to call it, interior QI. All we really mean is at bounded Hausdorff distance from one another inside of here, so therefore they're QI. So if each is in a compact translate of the other. Okay, now this tells you, this has actually been studied in some special cases because it has a lot of consequences for dynamics. If you have an action of all of GLNR and you restrict it to these subgroups, the fact that they differ uniformly by some compact thing tells you that the dynamics of those actions aren't too far off. And there's old results of Benedetti, some things by David Morris, although I think it was David Whitty at the time, doing this for some small examples. But the question of when groups can be close like this inside of GLNR is more or less completely open. Okay, there's a couple of obvious examples. They could be commensurable. That's the easy case. They could just intersect in a subgroup of finite index. They can be different co-compact lattices in the same closed subgroup. Okay, that also works pretty easily. But and then there are a few more exotic examples. But even this concrete question is pretty open. I know how to do it for GL2, and that's about where it stops. Okay, so.